Hello, everyone. Thank you for attending this talk. I'm Jiaqi. I'm from George Washington University. Today, I'm excited to present our work, DiTile-DGNN, an efficient accelerator for distributed dynamic graph neural network inference. This is a collaboration with Dr. Zheng and my advisor, Professor Ahmed Louri. Let's get started. Here is the outline of my talk. I will first introduce the motivation behind this work. Then I will present our proposed DiTile-DGNN design, including our redundancy-free parallelism strategy and the reconfigurable accelerator architecture. I will follow with my evaluation results and end with key conclusions. Dynamic graphs are everywhere. People use dynamic graphs to represent citation network, social network, or traffic network as the input of AI applications, such as Google Scholar, social media, or traffic prediction. Dynamic graphs are viewed as a sequence of snapshots. This one indicates a graph snapshot at time step 1. We add a vertex G to snapshot 1 to generate snapshot 2, and add an edge to generate snapshot T. The group of snapshots represent dynamic graphs. Graphs evolve over time, with vertices and edges being frequently added or removed. This dynamic nature poses significant challenges for processing and analysis, which is where our work comes in. Typical DGNN models integrate both conventional GNN and RNN kernels. For dynamic graphs, the DGNN model sequentially processes each snapshot to identify the changes occurring in the graphs. For example, the GNN kernel takes a snapshot G1 as the input, and it functions as a typical GNN model, which includes multiple GNN layers. The output feature vector Z1 is then fed into the RNN kernel to generate a hidden feature vector H1. For the following snapshot, they are also act as the input of GNN kernel. The RNN kernel uses its own output feature vector Z2, and the last snapshot's hidden feature vector H1 to generate its own hidden feature vector H2. GNN kernel is used to capture spatial information, such as the input graph structure. RNN kernel is used to process temporal information that captures the dynamic changes of graph representations. Most previous designs rely on centralized global buffers, or GLB. The left design faces three major problems. Low endpoint bandwidth due to shared memory access bottleneck, large memory access latency as all tiles compete for the same buffer, and poor scalability, especially in large P arrays. To overcome this issue, we adopt a distributed buffer architecture where each tile has its own local memory. This results in high bandwidth since each tile accesses memory independently, improves the local memory access due to the lower congestion, and overall better scalability as we scale to more tiles. The takeaway here is distributed on-chip memory enables better scalability for DGNN acceleration. Let's first introduce a commonly used parallelization strategy, temporal parallelization, where each snapshot is assigned to a separate tile. In this setup, GNN operations are local to each snapshot. So, in theory, no inter-tile communication is required for GNN kernel. However, this assumption breaks down in practice because the variation across snapshots is often negligible. Most vertices and their neighbors remain unchanged. As a result, GNN computation across tile becomes redundant, since they are repeating nearly identical operations on similar data. Furthermore, to capture temporal dynamics, each GNN output is fed into an RNN kernel, which processes temporal dependency, but the RNN in tile T+1 needs output from tile T. This introduces regular cross-tile communication, especially when there are a large number of snapshots. In summary, this approach leads to redundant GNN communication and computation among tiles, and high communication overhead for DGNN applications with long sequences of snapshots. Another commonly used strategy is spatial parallelization, where the graph is partitioned across tiles based on vertices. Spatially, the system performs two steps. Step 1 is partition the graph into several parts, for example, splitting the vertices site into multiple non-overlapping groups, and then assign each tile to process a specific vertex subset across all snapshots. For instance, tile 1 may be responsible for executing the first partition of the graphs in every snapshot. Building on the previous slides, let's further analyze the limitation of spatial parallelization in DGNNs. In real-world dynamic graphs, the variation between the consecutive snapshots is often ineligable. This means that the same vertices and its neighbors appear repeatedly with little change. As a result, each tile ends up reprocessing nearly identical neighborhoods across multiple snapshots. This leads to redundant GNN computation in different GNN kernels within the same tile, wasting cycles and memory access. At the same time, GNN aggregation requires features from neighbor vertices, which may be assigned to other tiles. Therefore, the GNN kernel must perform irregular across-tile communication to gather these features. This is particularly costly when the graph is dense, as each vertex is connected to many others across tile boundaries. But RN operations are local. No communication across tile is needed for RN kernel. So overall, spatial parallelization introduced two major problems: redundant GNN computation and communication, and high communication overhead due to the irregular cross-tile dependency in dense graphs. Let's now summarize what we have learned so far. We analyzed two parallelization strategies, temporal and spatial. Temporal parallelization enables local GNN execution but suffers from redundant GNN communication computation and regular cross-tile communication in RN phases. Spatial parallelization enables local RN executions, but also suffer from redundant GNN communication and computation, and irregular cross-tile communication during the GNN aggregation. In both cases, the key bottleneck is redundant communication and computation, and high cross-tile communication overhead. To address this, we propose a redundancy-free dynamic parallelization strategy. This strategy eliminates redundancy by reusing data across snapshots and dynamically chooses the best parallelization mode, temporal, spatial, or hybrid, based on the application's characters. But to support this dynamic behavior at runtime, we also need a reconfigurable accelerator architecture, one that can flexibly handle diverse data flow and communication patterns across different DGN applications. Our goal is to reduce the overall inter-tile communication overhead while eliminating the redundant communication and computation. To achieve this, we propose a redundancy-free dynamic parallelization strategy, which flexibly chooses two key parameters: snapshot power level factor, PS. This is the number of snapshots assigned to each tile. And vertices power level factor, PV. This is the number of vertices assigned to each tile. By turning these two factors, we can adapt the data flow to the specific structure of the workload. Here is a simple example. Let's say we choose PS equal to 2 and PV equal to 8. This means each snapshot is split into two parts. Each tile is assigned to process two snapshot subsets, covering a total of 8 vertices. Building on the previous slides, we now explain how our strategy reduces communication overhead by leveraging data reuse and adaptive tiling. The core idea consists of two parts. First, we eliminate redundant communication and computation by reuse intermediate features from ARM kernels, either within the same tile or from neighbor tiles. Second, we reduce inter-tile communication by flexibly choosing the snapshot and vertex power level factor depending on the application's characters. Let's look at two common DGN applications cases. For the dense snapshots, where many vertices are interconnected, we increase the number of vertices per tile. This helps minimize irregular GN communication across tiles. For long snapshots sequence applications, where the number of time steps is large, we increase the number of snapshots per tile. This reduces regular on communication by keeping tempo dependency local. By adaptively selecting the best tiling factor, both spatial and tempo, our strategy significantly lowers communication overhead across GN and RN stages while improving the efficiency. This figure shows the overall architecture of the DiTile-DGNN Accelerator. Our design includes 4 major components that together support dynamic workload, partitioning, and communication efficient data flow. Let me walk you through the system step by step, following the path in the figure. First, the host processor send the inference request to the request dispatcher. This is step 1. In step 2, the workload computation unit calculates the workload of each vertex based on the graph structure and model dips. In parallel, step 3, the parallelization strategy adjuster selects the best snapshot and vertex power level factors, P, S, and PV, using both the graph metadata and hardware resource constraints. These decisions are forwarded to the balanced and dynamic workload generator in step 4, which produce the logical partitions. We call this BDW groups. In step 5, these workload groups are stored in a reservoir. It dynamically feeds per tile workload into the execution pipeline. Before sending data to the compute tiles, we apply our redundancy-free unit in step 6 to eliminate unnecessary computation and communication by reusing results from previous snapshot. Now the system is ready for execution. In the step 7, the selected workload and the reuse instruction are passed to the reconfiguration unit, which programs the NOC interconnects to support different types of traffic, including the tempo communication for ARM kernels, spatial communication for GN kernels, and the reuse of where paths for cross-snapshot data reuse. Finally, in the step 8, the reconfigurable and distributed tile array RDTA processes the DGN workloads by pipelining both GN and ARM kernels, ensuring high throughput and low energy across iterations. To support the diverse communication and data flow needs of DGN workloads, we propose a reconfigurable and distributed tile array, or RDTA. The RDTA consists of a 4x4 tile array with tile interconnected via a reconfigurable interconnect, as shown in this figure. The interconnect uses a dual layer topology, horizontal links to form a ring. It is designed for regular communication, such as tempo dependency propagation in ARM kernels, and reuse of intermediate results across snapshots. The vertical links combine rings and reconfigurable links to support irregular spatial communication during the GN aggregation. These relinks connections are simple switchable transistors that dynamically enable bypass link between non-adjacency routers, helping minimize the hop count, reduce the congestion, and increase routing flexibility. Each tile integrates distributed buffer, a router interface, a 4x4P array connected via intra-tile mesh interconnect, and a reuse FIFO acting as a double buffer between PE. Each PE contains a local buffer, a macro-array, a data dispatcher, and a post-processing unit, like a ReLU. The DiTile-DGNN accelerator is designed to efficiently handle diverse data flow and communication patterns arising from the dynamic parallelism strategy across a wide range of DGNN applications by supporting both temporal and spatial parallelism or hybrid parallelism, and by dynamically adapting to graph density, snapshot similarity, and model structure. Our architecture eliminates redundant communication and computation, maximizes reuse, and delivers scalable performance on dynamic graph workloads. We now present the evaluation setup used to access the performance and efficiency of DiTile-DGNN. First, for the hardware modeling, we developed a cycle-accurate C++ simulator to capture fine-grained execution behavior and runtime. In addition, we use DRAM Sim2 for modeling off-chip DRAM power. Use CACTI-6 to estimate on-chip buffer power, both global and distributed buffer. Now let's look at the architecture configuration. DiTile-DGNN implements 16 by 16 tile array, totaling 256 tiles. Each tile integrates a distributed buffer, a router interface, a 4x4 processing element array, and a reuse FIFO buffer for inter-PE and inter-tile data reuse. The PE consists of a local buffer, a data dispatcher, a post-processing unit, a 4x4 multiplier array, 4x4 idle array, and associated control logic. As for the system parameters, the on-chip frequency is set at 700 MHz. The distributed buffer is 4 megabits per tile. The reused FIFO buffer is 512 gigabits, and each piece local buffer is 256 gigabits. We compare against 4 state-of-the-art accelerators, ReDI, DGN Booster, RISE, and Mega. Our benchmark including the graph convolution network with the LSM across real-world dynamic graphs dataset, including the pumped ReDI, mobile, Twitter, and other dataset. The DiTile-DGNN reduced off-chip memory access by up to 58%. This is primarily due to reuse-aware tiling and redundant computation elimination between snapshots. For the performance analysis, DiTile-DGNN achieves up to 56% execution time reduction as compared to ReDI, DGNN Booster, RISE, and Mega respectively. For the energy consumption analysis, DiTile-DGNN accelerator achieves up to 84% energy consumption reduction compared to the state-of-the-art accelerators. For the conclusion, DGNNs are widely used for achieving high interface accuracy in dynamic graphs-related applications. So we propose the DiTile-DGNN, including a parallelism strategy that can simultaneously balance the data reuse and parallelism efficiency of both GNN and RNN models. The parallelism strategy comprehensively considers the communication and the data reuse of component GNN and RNN kernels. And we also propose a reconfigurable and distributed tile accelerator architecture to efficiently manage the diverse communication requirements of DGNNs. The architecture dynamically configures the interconnect to handle both regular communication for temporal dependencies and irregular communication for spatial dependencies. The proposed design achieves higher performance and energy efficiency compared to the state-of-the-art accelerators. Thank you for your attention. I will be happy to take any questions.